the bar magnet and the magnetic field lines. See, if we have a bar magnet and if we sprinkle the iron fillings in the surrounding of it, then the arrangement of that iron filling in the surrounding of it will give you the magnetic field lines. Means, as per the arrangement of that iron fillings, you can prepare the magnetic field lines of that particular bar magnet. And here we can observe this thing, the magnetic field lines always form a closed loop. And if we draw the magnetic field lines by using these iron fillings or using magnetic needle, then we can observe this thing for the bar magnet and for short solenoid. The magnetic field lines are identical. Field lines form a closed loop for the bar magnet. It comes out from the North Pole and outside the magnet, it reaches to the South Pole. And inside the bar magnet, it is from south to north. In that way, it forms a closed loop. See, bar magnet, that is the magnetic dipole. So solenoid, that also we can consider as a magnetic dipole, because when current is passed through the solenoid and it produces the magnetic field identical to the magnetic field of bar magnet, means definitely one end of the solenoid that behave as north pole, other end of the solenoid behave as a south pole. But here if we think about electric dipole, then we know this thing. Electric field lines never form a closed loop. Electric field line comes out from the positive charge and end up at negative charge. Again, it will not move from negative to positive. So it will never form a closed loop. Clear? Then, if we draw the tangent at any point on the field line, then that will give you the direction of the magnetic field exactly at that particular point. Here in figure, you can observe the magnetic field lines and electric field lines for bar magnet and electric dipole respectively. Clear? Then, if the number of field lines passing through any surface area consider at a particular point that is more, then we can say in that particular area or at that point, the magnitude of the field that is more, or we can say the magnetic field is stronger one at that particular position. And if we consider the number of field lines passing through any particular area considered at a point, which one is very less, then we can say at that point the magnetic field strength, that is weak one. So number of field lines passing through unit area normal to it at any point will give you the magnetic field intensity at that particular point. Then we can say two magnetic field lines will never intersect each other, because if two magnetic field lines intersect each other, then at the point of intersection, you can prepare two tangents. It implies that at the point of intersection, two directions of the magnetic field will be there, which is never possible. Any vector never have two directions at any point. So in general, we can say two magnetic field lines will never intersect each other. That the same thing we discussed for the electric field lines also. Clear to all of you? Up to this one.